positively charged flexible chain that can absorb onto these macrons. And there are two possible ways it can absorb. Either at very large spacing, it absorbs to one of them. This is the simplest case. Complicated cases. Or it can bridge the space between the two, absorbing partly on one or partly on the other one. And in this case, you will see from this graph, this is the force between the macrolines as a function of the separation. You see that when it bridges the space between them, there's an attractive component to the interaction, and then it goes to zero. So this kind of interaction is usually referred to as the polyelectrolyte bridging interaction, and it's very important in various polyelectrolyte systems, also technologically important for interactions between macroscopic surfaces, as we will see. So once again, this is the situation, polyelectrolyte bridging. So you have a single chain that bridges the space between two macrolines, partially adsorbed onto both of them, and the part of the chain that bridges the space between them actually pushes them together, or pulls them together. And if it adsorbed on only one of them, then there's no such interaction. And obviously there's a transition between these two states at some critical separation, which is connected with the length of the polyelectrolyte. Because if the separation is too big, the polyelectrolyte cannot span the space, span the space between them, and of course it has to be signed. This is a little bit contrived, theoretical situation, but we can do better. We can do more realistic models, as we will see. But I will try to establish a connection with what Wei Yin does. Interestingly enough, that is possible with polyelectrolytes. And as a starter, we will try to formulate a theory for a situation depicted here. So one, let's say, positively charged polyelectrolyte between two negatively charged surfaces. The Hamiltonian of the chain is given like here. So it's got an entropic term and an interaction term. Interactions are Coulombic. And if we would have unconnected counterions, we would have the Poisson-Boltzmann equation. You remember that from my previous talk. And the boundary condition for the So the difference now is that these counterions are now connected. So one connected to the other one, and there's a sequence. There's a first monomer, second, third, and so on, in a series. The question is, how is this equation going to change? Is it still valid? And without going through the derivation, I can tell you that what you actually get are is a kind of a Schrodinger equation. If you describe the monomer density of the polyelectrolyte as proportional to some field square, psi square, and you call this the monomer density field, then this density field satisfies a Schrodinger-like equation. It's not imaginary as in, or complex in general, as in quantum mechanics, but it's a real number. Nevertheless, the equation is quite similar, as you can see. The Green's function for this polymer is obtained in this form. En, of course, is the eigenenergy. N signifies that it depends on the number of monomers in the chain. And the free energy of the system is proportional to the lowest eigenvalue of the energy, E0 times N. You all recognize this as very similar to quantum mechanics, except that the index N takes the role of time. Usually this is referred to as the Edwards rotation, meaning that if you take quantum mechanics and do a rotation into imaginary axis for the time, and you call the time the number of monomers on the chain, you get the same equations. So polyelectrolyte theory has a very nice correspondence with quantum mechanics.
So I just want to make sure, because I'm not. So that's En is in the form of a reduced potential.
En is the eigenenergy.
Yes.
So, yeah.
So we usually think that the other terms obviously are familiar with electrostatic energy. And what puts them on a card this way, I guess.
Yeah.
Is that the idea that you...
The idea is that you have now two equations. If I go just one slide further, there are two equations now.
Right, that's the
You
one.
recognize this as a, this is like a Poisson equation. But instead of the Boltzmann equation, you have this equation, the Edwards equation, which is like the Schrodinger equation. So you see that the divergence of E is proportional to the density of the counter ions, but the density of the counter ions is determined by the electrostatic field phi. So there are two coupled equations now.
Make me sleep better with the psi z squared.
Here?
Yeah.
So this is just the density of the monomers.
Yeah.
It's like the density of the counter ions. And in Poisson-Boltzmann case, you would say this is e to the minus e times phi. Yeah?
Right.
The Boltzmann distribution. Now it turns out this term you must get from this equation. You cannot write it simply as e to the minus. Yeah? But it turns out that you can write it like this, so it's an average value over all the polyelectrolyte configurations of the Boltzmann term. And if you just work this out, so this is a very compact notation, it doesn't mean anything. What is this average? Right? So if you work it out, this is what you get, two coupled equations.
You should give Adrian some chocolate.
That's the chocolate.
This is a definition of a paradox.
Yeah.
Who gives chocolate to the chocolate?
As it says on one of your cups. So this is a generalization of a simple Poisson-Boltzmann equation, valid if you have connected counterparts. That's the only difference. Everything else is the same.
It's linearized, so these things are small.
No, it's not linearized. It's a general, no linearization here.
What is the limit for the minimum length?
For the what?
For the minimum length of the chain?
What do you mean minimum length?
I mean, it's valid for if the contraries are connected,
Yeah,
and there should be
any size of the chain. Any. What?
2, 3.
You can do that. Yeah. So you get two coupled set of equations. One is, you can say this is the equivalent of the Poisson-Boltzmann equation, and the other one is the Edwards equation. This is like the Schrodinger
Psi
equation.
has some inverse length units here. Or something.
Psi is, so psi squared is the density,
Right. It's a density of...
charge density, actually. So if I go back, look at this equation.
Yeah.
The charge
Okay,
density
right.
is this is the charge per monomer
Right, I get it.
times
Yeah.
psi squared. That's the generalization of the standard Poisson-Boltzmann theory for connected counterparts. Very simple. Very simple. But difficult to solve, because now you don't have one equation that you need to solve. You have two coupled equations, which is of course more difficult. It turns out, I haven't written it here, you can solve this equation symbolically, yeah? And insert this solution in here. No, sorry, you can solve this equation by Green's function method, yeah? And you can insert it here, and you get the Landau-Ginzburg equation. So it has a first order term in psi, and then it has a third order term in psi. And that simply means, if you have some experience with that, that means there's a phase transition somewhere there.
There's a what?
Phase transition. Whatever that means is the context. But there's some kind of transition. Yeah, the question is, what kind of transition do we have here? In order to do that, we have to solve these equations numerically. Too difficult to do. I mean, you can't solve analytically. You have to do it numerically. So you introduce some length scales and rescale everything so that everything is dimensionless. For the electrostatic potential, you have the same boundary condition as in the Poisson-Boltzmann equation, but there's an additional condition that the integral of psi squared over the space where it resides has to be equal to the number of monomers in the chain. I just divided everything by the surface area. So we put S here and we get the volume. So what are the solutions like? Very surprising solution. And it connects directly, of course, to the phase transition that you need to have because you start with the Lambda-Ginsburg-like equation. So at small separation, this is the monomer density. So one surface is here, the other one is here. That's the monomer density in between. And I have rescaled all the separations so that they are on the same graph. So 1 and -1 are just the two surfaces. Yeah, but the separation varies. I just rescaled everything. So you see that at small separations, the distribution of monomers is what we refer to as monomodal. Most of the polymers of the monomers are in between. And there's a steric interaction with the system fields because you're starting to squeeze the monomers into a smaller space. So, but the distribution is monomal. And then at a certain critical point meaning critical separation, monomodal distribution becomes bimodal distribution. So part of the chain is absorbed to one surface, part of the chain is absorbed to the other surface in terms of the monomer density distribution. This is the Lambda-Ginsburg transition in this particular case. And in terms of the pressure between the surfaces, or the force, or the free energy, this is what we have. So, what you see here is, now let's see. So the minimum of this corresponds to, this is the free energy, and this is the pressure. You see that the free energy, here you have an attraction, here you have a repulsion, and when you cross the minimum, you just go from a bimodal to a monomodal flow. So if we look at the position of the minimum in the density, of the maximum in the density, monomer density, for various separations between the surfaces, you see that for small separations, the minimum is at 0, right here. Yeah, it's in the middle, and then all of a sudden, it starts diverging. Yeah, you go here, here, here. You go on another line. And this is like the second order transition. So this system displays a second order transition, which corresponds to absorption, desorption of the polymolecular chain to the surfaces. And while it absorbs and desorbs, it also changes the interaction from repulsion to attraction. So the repulsion is steric because you are squeezing the chain into a small space, and attraction is bridging. Part of it is absorbed here, part of it is absorbed there, and the part of the chain in between is just pulling the two surfaces together.
So when they're close, you're squishing the guys.
Yeah.
Repulsion. When they're far, they're trying to hang on to both.
Yes.
For some reason you have it symmetric, I'm not sure why. But it is, you said it.
So the next eigenvalue
And then as soon as they're trying to hang on to both sides with this equality condition,
yeah.
suddenly there's a tension because a certain number of them are not enjoying sticking.
Yes, exactly.
And that is the source, the stickiness, frustrated. And why is it symmetric?
Okay. So you can look at non-symmetric cases, of course, but it follows from quantum mechanics that the way the eigenenergy corresponding to a wave function with a higher number of nodes is bigger. So it will just have a bigger eigenenergy, asymmetric case.
Could you say that in real terms?
So there is, I mean, if you look at all the states, there will be, of course, also a state that's asymmetric, but it has a much larger energy than the symmetric state. So, because the free energy is proportional to the lowest eigenvalue, this is the free energy.
But maybe polymers didn't read quantum mechanics. Why would it be like that? I could easily imagine this guy saying, forget one of them, I'm going to stick to one.
So, you know, you can go to higher order terms, and you will have contributions from all these higher order, let's call them excitations, which are non-symmetric, solid. But their contribution is small. The bigger the chain, the smaller is their contribution to the overall partition function. It's like asking, you know, in Poisson-Boltzmann, why don't all the counter ions adsorb to the surface? That's one possible state, but there are other ones. And you have to sum over all of them, and then the contribution of this particular one becomes very small.
So, obviously, answering that case is entropy. And you're saying there are more ways of sticking if it sticks to more places. Is that,
I guess so.
is that okay
yeah.
to think like
I
that?
think so. Yeah. So I think of it in formal terms, lowest eigenenergy and then higher excited state, but again, that's the same thing.
But surely if you make the splitting energy big enough, it would worry anymore about entropy.
Okay. So this, of course, is the limit when the chain, the length of the chain, is much bigger than the separation between the surfaces. No matter what that is, the separation, it's always bigger. However, if you have a finite number of monomers, and the separation becomes big enough, then eventually, of course, that state, non-symmetric state, will get lost, and you will go to that state. Yes.
Really, what's A and A0 and AM?
A, I think, is the separation, and A0 is the, no, A is the position of the minimum, and A0 is the separation between surfaces. So I just normalize that.
Why is the point A equal to 2A0 is critical?
Yeah.
Why is that?
Why is that? So what you have here is middle divided by A0. Let's see what's A0. I can't recall what's A0. A0. So this is lambda. Lambda is defined. This is, maybe this is lambda. Yeah. So lambda is a kind of a constant that quantifies the strength of electrostatic interaction. And A0 is obviously 1 over lambda to 1/3. It's just a dimensional sequence. So now we go to, we want to be more realistic, so we go to a more complicated case. And the more complicated case, already very complicated actually, is many polyelectrolyte chains with also simple salt. So you have sodium chloride and a solution of polyelectrolytes. That's a system that's difficult to figure out already, but the basic equations you can write down. So the Edwards equation for the monomer density is the same, but the equation for the potential, electrostatic potential, you see that you have a Poisson-Boltzmann term due to the salt, and psi squared term, which is due to the polyelectrolyte chains. This is all highly, highly nonlinear, as you can of course see. This is quadratically psi, this is sinh nonlinear, and here you have phi times psi, also nonlinear. So it's a very, very complicated set of equations, and also, unfortunately, the parameter space is big. So you have kappa for the salt, you have sigma for the surface charge, you have charge per monomer for the polyelectrolyte chain, and you have the number of monomers. It's a pretty large parameter space. So there's no reason why anything simple should follow from the solution of these equations. Of course, you have to do it numerically. Also, there are problems to solve it numerically. It's not really. But qualitatively, you can distinguish several features in this more complicated system that are related to what we observed before for a single polyelectrolyte chain. So again, you have this second order transition, and you would expect there's a branch of attraction and a branch of repulsion, which is true, but the attractions and repulsions that do not correspond to this position. They are shifted. And they're shifted because in the overall equilibrium of forces, there's an additional repulsion, which is due to the salt. So it's more complicated. There is some relation to a previous case, but there's additional features. And one of the features is also that the pressure, so the interaction pressure, the force between the surfaces, can be non-monotonic in this case. Why? Because you have attraction from polyelectrolyte bridging on top of repulsion due to Poisson-Boltzmann. You sum the two together, you can see that you get curves like that. And of course, you have to take into account Maxwell's construction to get the equilibrium pressure. And that immediately means that in a system like that, two charged surfaces with salt, with polyelectrolyte, you have a transition between two separations in the surface, in the system. So the surfaces can be at one separation, and then they just jump into another separation. from here to here, along the maximum line. Very interesting, I think. And for all these behaviors, you can get the critical values of the parameters and the regions in the phase space where you can see those phenomena and so on. So I think this is it's a complicated picture, but nevertheless, interesting picture of what is going on in this case. As for experiments, Adrian probably remembers this guy who visited the lab years ago. And he was actually measuring this kind of interactions in his experimental setup. His experimental setup, you can see right here, so he has two surfaces. I think these are mica surfaces covered with something. Yeah. So it's polyacrylic acid and mica with salt. And he measures the interactions, and you see there's some attraction here developing. That's a jump into a different position, and he interpreted this in exactly the terms that, in the same terms as the theory. Actually, he took some expressions that I derived for the interaction and fitted it to his experimental curves. He got reasonable parameters. This doesn't mean that we can, explain all the details of his experiment, but in broad outlines, it fits. So I find this a very nice correspondence between theory and experiment. There are now other cases of polyelectrolyte mediated interactions, in particular connected with certain ordered phases in genosomes. Genosomes are complexes between DNA and lipids. We worked on that in the mid-90s. Everybody was working on that at that time because people thought that there will be huge progress in gene therapy. If you just mix lipids and DNA, you'll be able to do stuff. It turns out the only thing that was produced was a lot of papers on this particular topic. So this is the situation that you have. DNA intercalated between lipid bilayers, as you can see here, and making phases, liquid crystalline phases of various symmetry. So this is a lamellar phase, this is an hexagonal phase, and so on. DNA is condensed in a way with the counter ions, which are just lipid bilayers, positively charged lipid bilayers. So you need DOTAP, let's say, which is a positively charged lipid molecule. You make bilayers out of that, and because DNA is negatively charged, they of course associate in a certain way, and the equilibrium between energy, entropy, and so on leads to different phases. So this is the work. Dan Lasich actually was involved in that. We started many years ago. Unfortunately, he died a few years after that, and the subject was taken over by Sophia and his collaborators, which did a lot of cool work later on. We also have obviously very nice graphics from to show the nature of physics.
So in terms of the descriptions you're giving of stability, it didn't work for gene therapy because it was too stable?
I don't know what the problem was, but when they started injecting these genosomes into animals, it just didn't work as they
They transferred luciferase genes to the mouse cells, rat cells.
Yeah.
They were measuring the light coming out of cells.
Yeah. They got something, yeah, but not what they hoped for. If they would do what they were hoping for, that this would be a result issue, yeah, that they would be using it standardly. But it didn't work as it was supposed to work. So even Nancy, who was leading this effort at NIH, started to develop this. But at that time, there was huge hope that we are finally on the right track with this lipid DNA mesophages. Now you have, you can also do DNA viruses, you can make complexes between DNA and polyelectrolytes, which is what I want to address next, and so on. I'm not sure what the status of this field is now, maybe the comments more.
So I think some of these highly positively charged polymers are toxic. So
There you go.
that's a problem.
Yeah. And positively charged lipids, of course, are also toxic.
Yeah.
So, yeah, cure something, but that it's toxic. So, what I wanted, the connection I want to make here is between DNA arrays condensed with positively charged lipids and DNA arrays condensed with positively charged polyelectrolytes. So, related but different. In this case, the polyvalent counterions are, in inverted commas, are planar. In this case, there's flexible molecules spanning all the space between the polyelectrolytes. And this is the work done by Jason Rudi before he came to Adrian's lab. And he was using polylysine and polyarginine, very long, so these are very long, positively charged polyelectrolytes. The actual physics of the condensed phase is a little bit complicated because you can also have specific absorption of the polyelectrolyte chain onto DNA. Nevertheless, I would like to understand the packing of DNA with long polyelectrolyte chains in the same context as the forces between planar layers, planar surfaces, with polyelectrolyte chains in between. So I will try to make the same kind of theory for both. I will start with a hexagonal array of DNA, so it's a little bit like a two-dimensional crystal, right? You have an array of DNA molecules. If you cut this array with a plane perpendicular to their axis, you will get a two-dimensional hexagonal crystal. And in this crystal, I will insert long, oppositely charged polyelectrolyte chains, which you can see here. And the Hamiltonian is, of course, this is the entropy of the chain, this is the interaction potential, and I will assume, to start with, so no excitons, there will be no interactions between different parts of the chains, but there will be a strong interaction between polyelectrolyte chains and the DNA, and oppositely charged DNA. So my potential would be K0, this is the Bessel's function. You get K0 if you just integrate e to the minus kappa r over r in one direction. This is the direction of the long axis of DNA molecules. And you can do a lattice expansion for that, and so on. And it starts to look like electrons in a crystal. Similar equations. So the equations are right here. That's the equation we need to solve. So I was
Can
looking.
you go back a second? I got confused. Go back, please. So the blue guys have their charge.
Yeah, negatively charged.
The other guy has opposite charge.
Yes, positive.
You're coming in here with a Schmessel function, which is the interaction of the cylinders.
This is interaction between each subunit of the yellow guy with the blue guy.
You're treating it as the potential of the blue guy as felt by the yellow guy?
Yes, exactly.
So it's a passive kind of thing?
Yeah, exactly. So in principle, of course, I should add also interactions between the yellow guys and so on. But on the lowest order, I forget.
So the amount of charge, if you add up all the yellow charge and add up all the blue charge, is much, much less yellow charge. So he's riding on the blue guy's charge.
Yeah. It's an approximation.
No, I just want to hear what's pushing home.
It's an admitted approximation.
No, I'm not extracting confessions. I just want I want to be sure who's pushing whom around here. Okay.
So the problem, of course, is quite complicated, and you have to simplify it.
I didn't mean that in such a bad way.
No, I'm not apologizing. I'm just explaining what.
The yellow guy is riding on the potential of the blue guys without making a big curve.
Absolutely.
Okay.
So,
Rudi, why does the yellow polymer prefer to absorb some of its charges on one blue molecule and some of them on another blue molecule and then bridge them? Instead of like just grabbing each other.
This is exactly what's happening. I'm coming to it. Okay, yeah, you will see. So here, this is the equation. It does look a little bit like what you have in crystals, right? Wait.
Here.
Huh? It's similar. That's where you have the wave vectors of the reciprocal lattice and so on, except that it's a kind of a two-dimensional crystal. And you have to solve it, you have to get the eigenvalues and the eigenfunctions and so on. I will not bore you with that, but I will show you the profile of the monomer density for various limiting cases. Let's first look at this limiting case. So what do you see here? This would be DNA, one here, one here, one here, one here, one here, one here. Hexagonal array. Yeah? And wherever you have white stuff, this would be the density, high density of the polyelectron chain. So in this particular case, you will see that the polyelectrolyte density is mostly, so this is DNA, and it's in interstitial spaces, right? As opposed to this case, which is the same, DNA, 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 you see that there's a large density of monomers right next to the DNA surface. Here, it's removed to interstitial spaces between DNAs. But here, it's very close to DNA. And there's a little bridge here. Maybe you can see it, maybe not, but I can tell you there is one. Between these two regions here, these two regions, this, this, this. So it's, in this case, DNA is not, polyelectrolyte is not bridging the space between DNAs, whereas in this case, it is. And if you look at the corresponding dependence of the lowest eigenvalue on the density of the system, meaning on the separation between DNAs, you will see that in one case you have an attractive branch, and in the other case, in this case, you don't. Very similar to planar surfaces, but complicated by the fact that you have a hexagonal lattice.
I didn't understand what it does when it's not bridging from this figure on the left.
It's not, you know, here, something's going from one surface across to the other surface of DNA. And here, nothing's going in between. So this one is here, and this one is there. You know, there's nothing in here.
So one single chain is absorbed on one of the DNAs.
So you have to, the way you do the calculation, you go to very long chains. And you can actually treat this as one infinitely long chain.
And infinitely long DNA.
Yeah.
No, infinitely, of course, is assumed it's infinitely long in z direction. But the chain, the polyelectrolyte chain, is also. You can do everything finite, but I want to do the simplest thing. So you see that the overall features of this system are related to two surfaces, but just more complicated by the fact that you have a different symmetry of the lattice. This is not planar, this is hexagonal, and in some sense the polyelectrolyte chain plays the role of electrons in this two-dimensional crystal. There's more. Okay, these are the different eigenvalues. You see that the free energy, again, is proportional to the lowest eigenvalue for a very large chain. But there's lots of eigenvalues with various symmetries of the monomer density distribution, and we always follow the lowest one. So here's the lowest one, here. This is for different values of the parameters. And these are just some analytical expressions or limits that you can get for various eigenenergies in this system. Okay. Again, this case corresponds to non-bridging interaction between two macroions. In this case, corresponds to bridging interactions. So we are looking here, and here we are looking at the system in the direction of the long axis of DNA. DNA has hexagonal symmetry, and you see that in this case the polyelectrolyte chain adsorbs basically onto the surface of DNA, but then part of it bridges the region between two DNA molecules. So the system as a whole is interconnected with these bridges. And the question is,
DNA is considered as a cylinder.
Cylinder,
And
yeah.
here, some kind of sphere or particle.
Yeah, it's
But
different.
the concept is the same.
The concept is the same. Yeah. The symmetry and the dimensionality of the system is different, but the concept itself is the same. It's the same. So the question is, what is the magnitude of the interaction here and the range of the interaction when you compare it to this case? Is there any change? And why did we start thinking about that? Because obviously you see that here you have a whole spatial network of these bridges that is spanning the whole sample. So you would expect non-pairwise additive interactions to be important in that case, as opposed to this case where you only bridge the space between two neighboring particles. And indeed, you can see, there's analytical approximations that you can do, that the interaction goes as 1 over r squared. R is the separation between the macro ions, in this case DNA, in this model system, 1 over a squared. Whereas in this case, it's sort of exponential, so it's very short term. That means that by going from a two-particle interaction to a many-body interaction, connecting the whole system, you increase drastically also the range of interaction. That's perfectly intuitive, because if your bridges are spanning the whole sample, of course then the range of this interaction has to be pretty long. And it's 1 over r squared, so this is by definition a long range interaction. So we have two effects. We have the bridging interaction itself, which is providing the stability, holding the system together, but we also have non-pairwise additive effects which are providing a long range to this interaction. So this is another example of a very long range interaction. I'm not saying, of course, that in this particular DNA polyelectrolyte condensed system, these are the interactions that are operating, but they could be maybe in some related system. Maybe not this particular one, but some related system. It's an interesting phenomenon.
The salt is coming in really weird ways here.
Oh, there's no salt.
What's this kappa?
Kappa, okay. Kappa is, kappa is not kappa, it's something else. Oh, maybe it is
Sure
kappa.
looks like kappa.
It's
It's in there. It's the kappa that's in the argument, isn't it?
Right, right. Okay, yeah.
Okay, now answer my question.
Yeah. I'm sorry.
It's coming in really weird.
Why do you say that?
Well,
Which part?
if I can find the slide.
You slide onto this.
It's next slide.
Next time?
Yeah. So the second term, the salt was lost
Here. Yeah.
because the kappa.
It's just bridging. Yeah.
But there's something really amazing going on in the first term. You have
Yeah.
fourth power of kappa.
Mm-hmm.
What's going on?
That's the, it's a screen potential. So the strength of the bridging interaction should depend on the range of this potential.
But it's coming in kind of twice because you got measuring lengths in kappas,
Yeah.
and then there's some kind of a density you're measuring in kappas. Right?
Yes.
So is that that end term?
So there's, this W0, this is the strength of the interaction.
That's the sticky thing.
This is the range of the interaction. And they just come in this particular form. I think this is related to second derivative or something like that.
But the salt is coming in very, very strongly here, right?
It's coming in strongly. It should, yeah, of course. Because it's mediating the interaction. Without this interaction, you get nothing.
But it's doing two things. One is the mediation, the other is the sticking itself.
Yeah.
Is it not? The kappa comes into the sticking itself.
Right. Right.
So the more salt I have, the less the strength of the sticking,
Yeah.
and also the
So-
shorter the range when I have stuck.
W0 over kappa squared is a kind of dimensionless variable here. They always come together. You can see also here. So this is the critical strength of the interaction that gives you this situation as opposed to this situation.
Right.
Yeah? And if you divide by kappa squared, you see W over kappa squared, and kappa L is of course dimensionless also. And the same, W over kappa squared in this example.
Yeah, sure you can divide by kappa squared both sides, but you still have to be measuring your length in kappas. And that's what I guess is happening here. You're measuring your length in kappas.
It's all, everything is rescaled to dimensions.
I guess I'm asking a really easy question. Salt screens and also salt changes
The strength.
effective W.
Absolutely. Yeah, there are two effects. Yeah,
Yeah,
two effects.
that's the way I should think.
And
about
the
it.
interesting thing is that the dependence on R is not screened. It's not e to the minus something. It's just 1 over R. So that part of screening is lost because of the connectivity of the chain. But the part which is due to the direct chain interaction with the macrons, that part remains.
Yeah, that's reasonable. That's reasonable. Although, again, in that second term, the kappas are just canceling. out.
Yeah, it's just
I mean,
canceling.
think about it.
Yeah, this is obviously some kind of entropy.
Yeah. So what you see in real life is extraordinarily salt concentrations.
Should be. If it's this effect, it should be solved. So if you go further, this is just a different way to do the same calculation. Instead of bothering with the hexagonal symmetry, you just define a Wigner-Seitz cell, which is circular in this case, and you solve your equations in the Wigner-Seitz cell. This is the solution, and you get results that are very, very close to the, let's call it, exact calculation. We just did it to check whether everything fits. There's a critical value for the strength of the interaction. There's the energy or free energy dependence on the density of the system, and yeah. So what Jason sees in his experiments is that as he varies salt, sometimes he has these transitions. So this is osmotic pressure as a function of the state spacing for various salt conditions, and you see that in this case you start on one branch, whoop, jump, you continue to the other branch. These are pretty large spacings, and the position of this transition depends on the salt. It could be that maybe it's related to this kind of events. This system is just too complicated to come up with this simple.
On the amount of salt or on the?
On the amount of salt, yeah, on kappa, specifically, divided. So, yeah.
Rudi, in the previous slide, what is it? What? Rudi, slide, please.
Yeah.
No. Yeah, what is the difference between triangles and squares?
So these are different ion types, if I'm not mistaken. I forgot a little bit. So here you have sodium chloride concentration, but then you can have other counterions. So if you look at this one, this is the jump. Sodium concentration, spacing, and you see about pretty large spacings here. Polylysine being.
And the same amount of polylysine.
Polylysine. Maybe this is for polyarginine. Anyhow, the question now is, since we see this bridging attraction, and before I told you that in highly charged systems, you have a correlation attraction with polymetallic counterions, is there some kind of a connection? So what you start looking at is how does this bridging interaction change as you stiffen up the polymers, the polyelectrolyte. So this would be very flexible polyelectrolyte, and then you go to very stiff polyelectrolyte, like rods. And it turns out that as you look into the interaction pressure, you go actually continuously from the bridging attraction to the strong coupling attraction, just by varying the stiffness of the polyelectrolyte chain. So maybe there's a connection between the two. I think there is, at least in theory. And in string theories, people are talking a lot about duality, so-called duality. What does that mean? It means that if you have one theory or one model, and you calculate it for small charges, and you get a result, it turns out that there's a different theory that corresponds to very large charges, which leads to the same result. So strong coupling in one theory is the same as weak coupling in another theory. And it appears that the strong coupling for simple counterions is related to the weak coupling for long counterions, polyelectrolyte counterions, which I think is sort of, I mean, I'm not saying this is a deep result or whatever. I think it's cool. It's just cool to connect the two. So, this is pretty much it. This is what I wanted to tell you, and maybe I want to leave you with a nice message at the end, which is contained in this book, Gene and Cell Therapy. You know this book, Nicole?
Yeah, I heard about it.
Yeah? So we have a paper there on DNA, lipid, and polyelectrolyte, whatever, properties of complexes. And this has gone now through, this is second edition, actually a third edition is out already for a couple of years. And we are just beefing up our paper. It's like 40 or 50 pages now, we call. But it has neat stuff in it. I've been contacted every now and then by various people saying that it's really a great paper, very easy to understand, and so on. And our biggest fan is Thomasin. He reads and rereads it every year. Every year I get an email from him saying what about this, what about that. So we have very faithful audience for that.
But you did tell us Nancy dropped out of the game.
Yeah, she's doing, I mean, she's still in gene therapy.
And we haven't written a new edition in the last 3 years.
That's
putting the correlation with that statement.
So people say this is like the classic. And our paper on the stability of DNA lipid and the DNA polyelectrolyte complexes is described at great length in a very simple language, because of course this is a different audience. I cannot tell them about connectivity and Schrodinger. There's other language, but the results are of course exactly the same. So if you would like to learn more about this, everything basically I've been talking about for this last 3 lectures, you can check our paper in this book. And on this note, I